I'm Justin Walcrest, Director of Engineering and Operations with the Municipality of County of Cumberland.
I'm Pat Lewis. I'm the Manager of Municipal Engineering for the Dartmouth office at WSP.
We were honored to be recipients of this year's Lieutenant Governor's Award and are happy to be able to come and present the details of our project to you today. Our main project objective for the Pugwash Water Supply project was to provide a safe, reliable source of potable water to the residents of Pugwash and the surrounding area. Pugwash is a small community located on the Northumberland Strait on Nova Scotia's northern shore. It's located in the Municipality of County of Cumberland and has about 800 people. Some of the more interesting aspects of the village is it's home of the Thinker's Lodge. This is a National Historic Site that dates back to the first half of the 19th century. Conferences, workshops, and educational events have been held here continuously since 1955. The most famous conference was the first Pugwash Conference on Science and World Affairs in 1957. That led to a Nobel Peace Prize in 1995 shared by the conferences and by Joseph Roplat. The Nobel Peace Prize medal is on display at the lodge, and if you're in Pugwash, you can drop in and see it if they're open. Pugwash is a major employment hub for the area. The largest employer is the salt mine. It employs up to 500 people and exports salt all over eastern North America. It's the only underground salt mine in Nova Scotia. There are a lot of people that were involved in this project to make it become a reality. The project owner was the Municipality of Cumberland. We partnered with the federal and provincial governments through the Building Canada Fund to fund this project. 33% of the project's $15 million funding came from the Government of Canada. 33% of the funding came from the province of Nova Scotia. And the Municipality of County of Cumberland and a local improvement charge levied to the direct beneficiaries of the project covered the final 33%. Pugwash Village Commission was an integral part of this project. They provided local knowledge, a liaison to the community, as well we hosted many of our public engagement events at the Village Commission Hall. And of course, with any project like this, we'll have our engineers. WSP was contracted by the municipality to provide preliminary and detailed design work for this project, as well as construction management. Prior to their involvement, CBCL conducted a study of the private wells to determine water quality issues in the community. And Dylan worked with us on wellfield exploration and finding our water supply source. And there are numerous suppliers and contractors and staff that got us to where we were to have a finished product. So, why did we do this? Prior to the completion of the project, everyone in Pugwash and the surrounding areas were on their own private wells. In 2008 and 2010, community engagement was undertaken as part of the municipality's strategic planning. In 2008, the municipality's Integrated Community Sustainability Plan identified a reliable and safe potable water supply as an important need for the area. The plan, prepared with extensive public consultation, states, individuals, businesses, and industry all need access to clean water, and therefore the availability and quality of water dictates many, if not all, aspects of community planning. Without adequate water quantity and quality, a community is inhibited from future growth and development. In 2010, during the public consultation of the Pugwash Area Master Plan, it was noted that a lack of a centralized water system is perceived to have a negative impact on economic development in the area. And I quote, "First and foremost, the participants agreed that water, sewer, and other infrastructure is top priority. It became very apparent in order for infrastructure as a whole to be enhanced and projects to be undertaken, an improved water system is necessary." In the Pugwash Area Master Plan, water infrastructure was highlighted as the top priority and recommendation. And out of this public consultation process, we started to hear from the community that there were concerns with the quality of the wells they were using at the residences. My wells are salty. I'm concerned with the chemical constituents. So that it became a public health concern. So in 2012, the municipality started working with CBCL. We tested 10% of the wells in the Pugwash area. 80% of the wells tested had an exceedance in aesthetic parameters, and 30% of the wells tested above the health criteria for arsenic. There are other health concerns. Uranium was also present in a significant portion of the wells. Knowing this, it gave council a mandate to move forward with the project, with knowing there was a public health concern, on top of the consultation identifying that it was a barrier to economic development and growth in the area. So our next step was to find this safe and reliable source of water. We worked with Dillon Engineering starting in 2013 to identify an appropriate source of water. Criteria we considered were proximity to the village. Would the geology of that area be likely to bear water? Was it isolated so we could easily protect it and manage the source water area? While it's not completely the opposite, we need to make sure it's accessible as well as isolated. If it was accessible from a quad trail or a public or private road, that would have been a real benefit to getting in there and drilling the wells. We want the site to be non-goody, and we considered land ownership. It was owned by the Crown or the municipality already, or someone known to be supportive of the project. That would have played a factor in selecting. So we drilled over 15 wells in 6 different locations. Some of them are based on the criteria seen there. Others are through local knowledge, where we'd hear from a farmer that, oh, in back the Irish Town Road, we've always had good water. There was a very accessible private road, and we went back and tested it, and that one didn't bear the quantity of water we required. In the end, Site 3 in the Rockley area was the successful site. It was the last site we tested because while the geology was the most promising to yield water, it was the least accessible of all the sites. So the final location, Rockley, here's Highway 321, and this yellow line here through the middle is a quad trail used by local ATV and snowmobile groups, but we upgraded a lot of that through the well area. We have 3 production wells drilled, and the black line around the edge is the area that's owned directly by the municipality. We purchased around 100 hectares that essentially represents the 2-year capture zone for the source water area. We have put into place a source water protection plan and are working with the province and our source water protection plan committee to establish this as a designated water supply. And that work is ongoing. Pat, I'll turn it over to you.
Thank you, thank you, Justin. So I'm going to take you through, I guess, when WSP became involved. Once the municipality had secured a good location for the quantity and quality of water that they're looking for, they engaged WSP in the preliminary and eventually the detailed design on the project. So when we became involved, kind of a few things that we wanted to look at to build this project really from the ground up was the water demand. We had to look at the village core and how many users we were going to have. We had to go look at the wells to ensure that they were indeed of the quality and quantity, and you know, if we could protect them and stabilize them. As Justin mentioned, the site was not the ideal location as far as accessibility, so we had to ensure that we could indeed access the well field and supply power to it, since it was sort of in the middle of the woods. Next thing we considered in our preliminary design is if we could achieve a location for a reservoir and what size that would be. And then the next step was to look at the treatment based on the at least initial data that we had on the well quality. And finally, we had to get the water to the residents, so we had to develop the distribution and transmission network. And finally, obviously, you need to keep in mind project budget and schedule based on the funding that the municipality had in place. So I realize this map is kind of difficult to read, but it kind of gives you the scale of the location and I guess the distance from the well field to the town. So in the left-hand corner, highlighted in sort of the black circle there, is where the well field is located, and then the inset you can see where the town or the village, which is where the bulk of our users are going to be. So it's quite a long trek to get to the well field all the way into the town. The major roads are sort of up on the more towards the I guess the top left-hand corner. And the blue line was eventually the route that was chosen. And this is actually through a sort of an existing woods road. it wasn't ideal, and it required upgrading, but it was sort of the most direct route to get to our first customer, which is located near the center of the page. So as I mentioned, based on what the municipality felt was going to be their core area for users, we had to establish what the demand was going to be, to essentially design the entire system around that. Now, since everybody was on wells, we didn't have any historical data on consumption. So we had to look for other sources. We went to industry guidelines and other utility design guidelines. We looked at consumption records for neighboring communities who were on a public water supply. We took into consideration that there is a trend for low flow fixtures. So, we're starting to see those numbers drop in particular on residential users. We had to consider that not everybody was going to connect, and it was going to take some time for everybody to connect. It wasn't sort of a 0 to 100 on day one. We also had to consider that the nature of Pugwash, it's a community that has full-time residents there, but is also a seasonal aspect to it. So there's more and more people that are going there for the summer months, or as long as their summer is, I guess. So there was the seasonal residents who may or may not want to connect. In addition, we had to consider if fire flow was going to be provided, because this can have a large impact on the infrastructure and the sizing of the infrastructure. So really, from day one, the municipality made the decision that fire flow was not going to be something that was provided to the community. Their focus was on providing clean, potable water to the residents. There's a mix of users there. Predominantly, it's a residential community, but there is some small commercial, space there. There's some industrial and institutional users, which was really good for us in the sense that, residential, the demands aren't that high, and sort of having a few anchor users that would likely hook up on day one was ideal for the system. So, the users there are like the Sunset Adult Residential Center, the Eastern Cumberland Lodge. As Justin mentioned earlier, there's the Canadian Salt Company, there's Seagull Pewter Manufacturing, and Northumberland Cumberland Memorial Hospital. So through all that, we developed what we, based on, like I said earlier, the standards that we had and the information we had from neighboring communities, we developed what we anticipated as being the average day demand of about 370 liters per minute, with a max day demand of about 980 liters per minute. So this was kind of the foundation when we're going to move to our design of the system. So again, back to the wells. They were developed a few years before we got involved, so we had to go back and revisit them. We had to ensure that they were still adequate, that nothing happened to them sort of during that period when they were dormant. So we, first thing that we did was we did a downhole video survey of the wells to identify if there's any issues with them. And we noted that the type of geology that was there, the sedimentary bedrock sequence that was observed, it was kind of fractured and brittle and broken. And when we looked at the water, the raw water results, we were seeing some elevated levels of turbidity in at least two of the wells. And this was initially a little bit of a concern to us because of the various types of treatment technology that we were considering. Turbidity could be a bit of an issue, and you may have to look at trying to reduce that or filter that out in advance of the treatment. So the first thing that we attempted to do was to reduce that in the wells. And our solution to that was to remount the wells and install a PVC liner that had solid sections and sections with slots in it. So the whole idea of this was that the PVC, would sort of protect the wells from the turbidity or the sediment getting in the wells, as well as the placing of the pump itself was to be in a section that was a solid section, so that would reduce the turbulent flow within the well. So you can see a couple pictures of us, upgrading the wells and sliding the PVC liner in place. Next thing, again, as we mentioned earlier, site access was, I wouldn't say a concern, but it definitely was a challenge for the site. There was an existing woods road, and I'll use that term lightly to get into where the wells were. You wouldn't take your Tercel in there by any means. But it was, accessible to at least to get into the sites to do the drilling. But in long term, it wasn't ideal. So we had to take that access road and upgrade it. It was about 1 kilometer long. We also had to obviously get power into the site. We needed power for the wells. We needed power for the treatment plant, which was going to be located sort of in the center of the 3 wells. That identified another hurdle for us. Like many parts of rural Nova Scotia, 3-phase power is not readily available. In most areas, it's single-phase power. Now, I'm not an electrical engineer, and I'm not going to attempt to pose as one, but it was I guess an issue, because typically when we're looking at treatment equipment and pumps, 3-phase power is ideal. When we looked around the area, the closest 3-phase power was about 12 kilometers away. There was a few different options there. One was would possibly involve routing that would, we would have to cross a river, which poses a whole other level of approvals and challenges. So we went back and said, can we utilize the single-phase power and not have to have this additional capital cost for continuing or extending the 3-phase power to the site. So the way around this is to use VFDs on all the equipment, the pumps and all the other mechanical equipment. So by doing that, we're essentially converting the single-phase power to 3-phase power. Again, pros and cons with this. Initially we lowered the capital cost of the power supply, but we increased the capital costs a little bit for the operating equipment. And there's a bit more operating costs associated with the VFDs as well. But the upside is that, particularly with the pumps, the VFDs provide us that additional control over the frequency of the pumps, which help us better regulate the flow to the treatment plant. So in the end, that was the solution that we chose to ensure that the plant continued to have power during outages, as Justin alluded to earlier, during Dorian last year, when essentially the entire village was without power. They were able to still supply water to the community because we had a backup power generator at the station. So next, we were looking at storage and if we could achieve storage at the site. Again, if we look at this map, the wells and treatment plants are on the lower left-hand corner. Bulk of our customers are on the right-hand corner. The route that was through the sort of cross-country through the existing road that was there, we identified sort of a high ground about halfway through that was really the perfect location to put a tank to give you that additional elevation for the hydraulic grade line. Downside of it is, again, it's in the middle of nowhere. So if we needed power at the site, that was going to be a challenge. In the end, that was the site that was selected. So sort of just near the middle of your screen there was the site that we selected for the tank. So this is a little picture of the tank here. We had to size the tank accordingly, and essentially the tank is sized based on the hydraulic grade line required. So there's an element of dead storage there to elevate the column of water up to get the hydraulic grade lines to achieve the pressures in the town. The next thing that the tank provides is emergency storage. So if in the event that the treatment plant is down for some reason, we're still able to provide water to the community with emergency storage for at least a day or so. In the end, the tank worked out to be about 20 meters high. The volume is about 1,400 cubic meters, and it's a Griterio glass fused bolted steel tank. And as I said earlier, power was not readily available. It's about 2.5 kilometers from the treatment plant, or 2.5 kilometers from the nearest road. So we looked at solar power as providing the power. We didn't need a whole lot of power there, but we did need to provide power for the instrumentation and control so the tank could communicate back to the treatment plant. Next couple pictures here are showing the construction of the tank, and I found this, kind of fascinating in the sense that the tank is actually constructed from the bottom up. So they place the panels, they bolt them together and jack the section up. So they actually build the top of the tank first and jack it up from the bottom until eventually they reach the full height of the tank. So you can just see a couple of pictures there during construction, and then the final product for the tank. It's quite a nice looking tank. It's still nice and shiny and blue. One of the, I guess, most tanks, they often have the community name on the side of the tank, and we considered that, but when we sort of did a mock-up, it wasn't really, you couldn't really see it from anywhere because the tank was so remote. So we didn't end up putting the village of Pugwash on the side of the tank because it was only, I guess you could only see it from a distance. So that's about it. Yeah. Another shot from the sort of the aerial view of the tank, so that gives you the the perception of sort of there's not much around it, and there's our communication on it, and a nice shot inside the tank. So now we have a well supply and we have storage. Treatment was the next point of consideration in our design. Based on the data that we had, on the quality of the water, we had two areas that we had to treat for, and these are aesthetic in nature. It's the iron and manganese. Generally, the water is good quality, but has elevated levels of iron and manganese to meet the guidelines. So we looked at having a pre-qualification of treatment processes because we wanted to consider the various types of treatment processes out there in our design. So we did an RFP for the treatment equipment. And the considerations in the evaluation were obviously had to treat for the iron and manganese. It had to have the ability to have redundancy in the treatment train. So if for maintenance reasons or something else that one of the trains was down, we had to still keep the plant operating. We wanted to be able to pump directly from the well field through the treatment process right to the tank without having it to require any type of storage at the treatment facility. Capital costs obviously factor into it, and it was very important the municipality to consider the long-term operating costs because of their funding models. So, they had available funding for the construction, but at the end of the day, once things are operating, the long-term operating costs are on the utility. In addition, because of the plant not sort of being operated, having a full-time operator on site, it had to be fairly easy to operate. And again, with the accessibility challenges of getting to the site, you had to have that remote capability. They had a desire to minimize the chemical additives other than obviously chlorine. And the other thing that we considered it was the backwash water requirements to minimize the stress on the source supply and any type of disposal challenges, again, considering where the plant was being located. So the next picture here is the construction of the treatment facility itself. So we needed a building to house the equipment. We chose a sort of a low maintenance type of construction. These are PVC panels. They're sort of, the formwork and all in one. So the panels, snack together sort of like, I guess, Lego or IKEA. And concrete is poured in the panels and you have a finished surface already on the outside. So it provides great long-term maintenance or low maintenance. And for the inside of the plant, if you need to sort of spray anything down, it's ideal for that. And again, bulletproof. Again, an odd consideration, but it is definitely a consideration on this project. Not that everybody in Pugwash is toting guns, but you know, like I say, it is an area that there could be hunters and people like to take target practice. So, you know, again, I recognize this is a little busy and you know, maybe challenging for you to see on your screens right now, but this is the process flow diagram, you know, for the treatment facility. Again, I'm not going to say that I'm a treatment engineer. We had experts on our team that I guess, you know, helped us with the design on this and helped us with the evaluation and the selection of the treatment type equipment. So in the end, we selected a two-stage Ferrazor Magnazor biological pressure filter system by Suez. This Ferrazor is the first of its type in Nova Scotia. So I said it's a two-stage. The first stage is 2 Ferrazor filters for dissolved iron. The second stage is 2 Magnazor filters for dissolved manganese. And essentially the science behind it is there's naturally occurring bacteria in the water that adhere to the filter media and they produce a biofilm. The BioLite is the patent filter media by Suez. Process air is injected to promote growth, and you can add sodium hydroxide to adjust the pH balance in the water if need be. The biologic oxidized metals form like a really kind of compact precipitate that are incorporated into this biofilm and essentially strip the iron and manganese out of the raw water. Again, it's maybe for a lot of people, this may seem like a bit of an unusual type of treatment process, but it's worked quite well, quite successful in other areas. And again, it was really selected based on a very low maintenance, low need for chemicals. We obviously add, you know, we chlorinate the water after it's been treated. So the sodium hypochlorite is added after the water comes out of the treatment plant just before it heads to the reservoir. Next couple of pictures here are just kind of some pictures within the treatment facility. The one on the left there is the media, and on the right there you can see some of the tanks. It's fairly compact. It kind of, you know, arrived in pieces and was put together and commissioned. You know, fortunately it fit in the space. And was like I say, was selected really based on its ease of operation. Now we have water, we have treated water, we have somewhere to put it, we have to now get it to the residents. So we obviously need a network transmission and distribution network to achieve this. So again, if you look at the map there, the blue line running from the treatment plant out to the village core is what we termed as our transmission main. And then once we get into the village core, we went through a distribution network, which is where the bulk of the users are. We ended up adding a little bit of extra customers after the, I guess after the first phase of construction out towards the Gulf Shore. We added, I believe, 35 additional customers out there that are year-round and 15 seasonal customers. Our first customer is actually at the Old Murray Road here. So again, just about the center of your screen before you head across the harbor. The nature of the area is that we really had kind of 3 distinct areas of I guess, water main installation. So we had the inside core area of the village, and it's kind of your traditional rural village with, you know, compact streets, a grid network. There is sanitary in the village, so we had to deal with existing infrastructure that was there and locate our water main accordingly. There was some cross culverts and so a little bit more confined. We had the area outside the village, and I should add that all of these roads are actually owned by TIR and not the municipality. So we had to work with TIR to get their approval and acceptance of the water main. Generally outside the village, the water main is located at or near the shoulder of the road. These are all sort of your typical roads, rural road cross section with ditches. And then we had the section just to the right there, which is so I guess the main transmission main from the treatment plant out to the Old Murray Road. And really this was, since there was no services along this section, it went in pretty slick. We actually used HDPE fuse pipe, and they used a trenching machine to install it. So they would fuse the sections of pipe together on the surface, and then roll it into the trench. Couple little, I guess, design considerations along the routing is we had two bridge crossings actually. So you'll see a picture there at the Palmerston Bridge. So we, in our initial stages of the design, we considered if we would directional drill, which was a fair distance across the harbor there, and would also come with some pretty significant challenges based on the geology. So we did weigh that out and weigh out the cost of that, but in the end we chose to hang the water main off the bridge. It's obviously, since it's exposed, we've insulated and heat traced it. So that was at Palmerston Bridge, as well as we had another water course crossing with a bridge at Tides Mill. In addition, through the woods section, we had a few water courses that we had to deal with. So rather than disturb the water courses, and because we were using the HDPE pipe anyways, we chose to directional drill these water courses. So this minimized the disruption of the water courses and minimized the permit requirements related to that. Well sites, buildings, and pumps. We have our wells. We have to provide equipment at the wells, controls and whatnot. Again, back to the bulletproof question here. We put structures at each. These are precast Shaw structures that were put at each one of the wells, as well as the chlorine booster station between the tank and the first customer. These are sort of little huts that came together and kind of look like something out of Fred Flintstone, but they snap together pretty well and are pretty secure structures and provide the space for the mechanical electrical controls. Installation in the wells itself, we selected our pumps. We have 3 wells that are currently operating. We have a 4th well that is available. It should be required in the future for further development. We installed submersible turbine pumps with pitless adapters. So once everything is installed, it's sort of all below the surface. The pumps, 2 wells are similar in size. So the pumps are 15 horsepower, and the smaller well with lower yield was 10 horsepower. So they provide about 5 to 7.5 liters a second. As mentioned earlier, our strategy in the design and construction was sort of a phased approach. The municipality was really keen to get construction going as early as possible. So we looked at various aspects of the design that we could advance relatively quickly and get out to tender, and at the same time continue on the design process of some of the other features. So one of the first things that we put out to tender was the treatment plant access road, and that was ideal to get that constructed right away. It provided easier access in when we were doing the rest of the work as well for the wells and for the treatment facility. The next tender we put out was the transmission distribution network. We followed that up with the water storage reservoir. And then we did a separate tender for the building and site works for the treatment facility. And then finally, we did a tender for the water treatment plant and wellfield development itself. So that's sort of the guts of the plant, and then the wellfield development to sort of connect everything together and have a fully operational system. So definitely some challenges in that approach. You're still doing design at the same time as things are being constructed, so you have to have some confidence in your preliminary design and try to avoid any adjustments along the way. As well as you're dealing with multiple contractors that all have to kind of connect everything in together. So there has to be a great level of coordination there. This is just a kind of a screenshot of the screen showing the monitoring of sort of all the pieces of the puzzle that came together. So you know, we have our monitoring of the wells, we have the monitoring of our treatment facility, we have some data there on our tank, and then our chlorine booster station. So all this can be controlled at the plant as well as controlled remotely and monitored remotely, which is again ideal for the municipality to have that access. Some facts and figures, some basic facts and figures once the project is kind of wrapping up. Our average water demand was about 985 liters per minute, so the system was based around that. At the end of the day, we installed 24 kilometers of water main, and 336 services were installed to the property line. So we installed at every resident. We installed a service there to the property line, and then ultimately it's up to the resident to come in when they're ready and make that final connection from the property line up to their home. The storage or the treatment facility, as I said earlier, is a two-stage Ferrozor Magnezor biological pressure filter system by Suez. The storage tank is 1,400 cubic meters, and the capital budget for the project was $15 million. And Justin, I think we stayed under that budget by a hair.
And we spent every penny up to the budget.
So we utilized that budget to provide them the best possible system that we could. So as you can see, a lot of collaboration had to happen on this project. We have the municipality as the owner. We have the government of Nova Scotia through TIR as the owner and operator of all the roads within the facility. We have them also as well as for any type of permitting requirements for the water supply and environmental permitting for the construction. We have the WSP team over there on the side, and this was a large team to pull this off. We have our environmental group who took care of the environmental approvals. They did the additional hydrogeology studies. They conducted geotechnical testing and performance testing during construction. We have our buildings team, which was responsible for the instrumentation and controls, and our electrical and mechanical for our buildings. And then our infrastructure team, which was responsible for geomatic survey, and sort of all the design of the access roads, the structures, the water mains and water tanks, the water treatment process. And then obviously we need somebody to build all this. And as I said earlier, there was a lot of people involved here, several different contractors. So Dexter was probably the largest contractor and had the lion's share of the work. Suez was the supplier of the treatment facility. Griterio was the tank. Spear was the construction of the treatment building itself and site works. McCormick & Sons did the access road, and Black & McDonald was sort of the contractor for all of the instrumentation and controls. Again, a lot of collaboration involved here. Okay, and I guess finally, Justin.
So where are we now? After, I guess we'll call it a challenging commissioning process, when we finally convinced the site inspector to stop licking the sample bottles, we got all our good bacteria samples in and had everything chlorinated. We had a lot of entrained air, which took a while to sort through and not have our water look like vanilla milkshakes, but in May of 2019, we were able to connect our first customer to the system. It was in fact the Village Commission Hall the night of their annual general meeting. Throughout the process, I was giving annual updates at these meetings, of course, with more regular updates to the communities as we were going, but At this meeting, I indulged in a bit of showmanship. When I was asked to give my update, I walked to the back of the room, poured a pitcher from the tap, and poured a glass of water for each of the commissioners, the warden, and the MLA, and said, "The water's on." And then we're off to the races. Currently, we have 155 customers connected. That's about half the total number of connections, but we do have the Sunset Adult Residential Center, which is a home for people with cognitive disabilities, and the East Cumberland Lodge is a seniors home. So these two big institutional users help us get to, well, only half the connections. We're using 60 to 70% of the total system volume. We're hoping over the next few years we'll get up to 90% plus of our potential customers. We're hooking up a dozen a month. We got slowed down there in March by the ongoing global pandemic, but it's been steady throughout this summer. We were able to install water meters this July and August, working with Neptune, using a lot of safety precautions. We entered people's homes and had more than 95% compliance with the public wanting to have the water meters installed. So that was very exciting. As Pat stated, this was a project that required a lot of collaboration. We had lots of municipal staff involved in this, from the engineering department and the operations department, working with the contractors, consultants all the way along to make sure the plant was commissioned. They had a good understanding of how to work the infrastructure and how it all went together. So it was no one person. There's no heroes in this. It was definitely a team effort, and we're really proud of the results that we can offer the community, and as stated, fix an identified public health concern. So very proud of the process going forward, although I was a persona non grata when we had most of the community shut down with long waits for a couple different pipe crews going at once. Really, the community is very supportive of the project, more often than not bringing cookies and goodwill to the pipe crews than giving them multiple fingered salutes. So very happy to have this done, very happy to have the support of the community. Pat alluded to Hurricane Dorian being a big driver for connections. The power, Pugwash was hit particularly hard. A lot of trees were down. The power was off for 4 or 5 days. Those early adopters of the system had water the entire way through, and I think they were a little smug about that. But it served to be a good advertisement for the benefits of the water system and the further going forward. So very excited, very grateful for everyone that helped make this a reality. And again, thank you to Engineers Nova Scotia. We're honored to receive the Lieutenant Governor's Award this year. And thank you everyone for listening to us. And on that note.
So I guess this is saying that now in Pugwash, you can wash your pug. And Justin is going to give you a bill, though. So obviously this has to be supported for the future. So we have some time now, I think, for some questions. If you want to type out your questions, and one of us will read them off, and we'll do our best to answer them.
We've stunned them into silence, Pat.
Apparently so. All right. If there's no further questions, there's just one thing I'd like to add at the end here. This is a photo of myself, Micah Pellegrino, our process engineer, and Ivan Bishop. This was an award that we received from WSP for Municipal Project Engineer, Project of the Year last fall in an award ceremony in Toronto. Sadly, Ivan passed away in a tragic accident last February, and I think everybody that's familiar with the project knows that Ivan was a huge part of the project, and I just wanted to really recognize his contribution to the project here.
Yes, thank you, Pat. I'd like to echo that. You know, Ivan was integral. Whenever we had a question, if Ivan didn't know the answer, he knew who he could get it from. And holding us to the fire on our timelines and the contractors to the contract, his contribution to the project was necessary, integral, and he's definitely missed. But we do have a question now. from Bruce Walker, and I'll read it out, Pat, and you can try to answer it.
Okay.
The manganese and iron removal process is intriguing. I believe you says it requires air to be injected into the water, and I presume it is aerobic. Does the same biological removal process tend to occur in a dug well that is open to the air and allows time for the process to occur?
I would, like I said earlier, I'm not the process engineer. I don't know if this was sort of ever utilized for a dug well type environment. I guess the component of the treatment process, as I understand, that's key, is the media that's there. So I'm honestly not sure how it would work in that type of situation, but I'm sure if we brought this question to Suez, they could probably answer it for you.
Just a bit more context. The media isn't seeded with the bacteria. It is naturally occurring in the soil and the groundwater. It just provides a home in a circumstance that they're happy to exist in.
Yeah, and, it's essentially like a host for it. So.
Any other questions? All right, going once, going twice. Oh.
All right then.
All right. Thank you very much, everyone.
Thank you so much.
Have a great day.
Bye.